Hello, dear colleagues and everyone who is interested in microwave technology. Welcome to a series of lectures dedicated to radio wave propagation and antenna technology. Today we are going to start with the first lecture, and then we are going to meet on Wednesday every week for about 2 months or so. For those who don't know me, let me introduce myself. My name is Anton, and I'm working as a technical support engineer at Softechnica. For some of you, it's almost the end of the work. For example, for Denver colleagues, it's an early morning, so good morning to them. And I hope that you will enjoy these lectures and find it useful, refresh your knowledge, or get some new insight into physics underlying the propagation of radio waves and antenna basics. Also, you are welcome to ask your questions. I can see them here on my screen, so please use the chat, which is available in the YouTube. And also, after the presentation is over, you can take a chance to take a quiz to test your knowledge. And for those of you who will attend all the lectures and will complete all the tests, we will select the best and will give him some prize from our side. So, what do you expect from this course? The course is divided in two main parts. The first part is dedicated to radio frequency basics and radio wave propagation, including the following subjects. The first one, which we are going to cover today, will be dedicated to electromagnetic wave main characteristics and the signal standards. Then we're going to look into propagation properties of different frequency range radio signals. And at last, we will see different types of propagation in the atmosphere. The second part will be dedicated to antenna basics, including two subjects. The first one is the main antenna characteristics, and the second one, different types of antennas. So let us start with the first part, which is electromagnetic wave main characteristics. So to speak about the signal propagation and microwave signal in particular, we'll have to generally review the radio waves physics. How do they propagate and what are the main properties of these radio waves? Therefore, the first part will be dedicated to the electromagnetic waves in general and to their main characteristics. You may have already learned this in high school, you may have used it throughout your work, or maybe not. And for some of you, there will be some new things probably. For some, everything will be already known, but just to refresh your knowledge, I hope it will be useful. And some interesting facts maybe you will find. And to begin with, let me ask you a question. What are these equations you can see on your screen and also here on this board? So I'm waiting for your suggestions, for your answers in the chat. Please let me make it as much interactive as possible, because that way it would be interesting for all of us. So now I will take a pause. I wait a little bit for your suggestions. And please don't be shy and share your suggestions. What do you think are these equations about? Yes, that's correct. This is the surname of this person on the right. And Anton gives us the correct answer. This is Maxwell, James Clerk Maxwell, a Scottish mathematician and scientist who worked out the 4 equations you can see on the board. and these are called Maxwell equations, namely the four of them. The first one is Gauss' law for electricity, the second is Gauss' law for magnetism, the Faraday's law of induction, and finally the Ampere's law. Here you can see the differential form of these equations. Actually, there is another form, which is integral form, and to be honest, I like it better. So I'm going to show you this form, and then we'll get to the integral form to see how these equations could be applied to the real world, to the engineering. Maxwell-Heaviside equations. Well, someone from you also mentioned another scientist who was involved in the in working out of these equations. Heaviside, he was the one who formulated these four equations together with other scientists out of the 20 equations which initially existed. But that was just one of these scientists. There were also others, like Heinrich Hertz, for example. But it's good that you know the other name of these equations. So these equations basically describe how do the electromagnetic wave propagate through the space. These are symmetrical. They describe both the electrical field and the magnetic field. And what do we see here is that they depend, actually let me select a pointer. What do we see here? Actually, we see that the electrical field originates from the electrical charge designated by ρ, which is electrical charge density. So there is electrically charged objects which generate the electrical field. And this is electric induction. The second one describes the originating of the magnetic field. This is magnetic induction. We can see that this is equal to 0. What does it mean? It means that there are no magnetic monopoles or magnetically charged objects, in contrast with the electrically charged objects. We will explain this in a little bit more detail further on when we will review the integral form of these equations. And also it's worth mentioning that all the fields, both electrical fields and magnetic fields, can be described using the terms of rotation or curl and divergence. And these operators actually are the divergence operators. The first two are divergence operators, the third and the fourth are curl operators. And this is how the fields are described in space. And this is three-dimensional gradient operator in front of each of these equations. We can see that one source of the electrical and magnetic field is the charges themselves, and also the other source is the moving charges and currents, which are shown also here in the last equations. This is the current density. Additionally to the charges and moving charges, there are the fields with time variation in one field which produces the other field. This is the second source, the second main source of the fields as well. And this can be well seen from the third and fourth equations. We can see that the changing magnetic field produces electric field, and vice versa. Changing electrical field produces the magnetic field. So there are charges, there are moving charges or currents, and there are time variation in the fields. These all are the main sources of the electrical and magnetic fields. And this is what these equations are about. this differential form of the equations, which are shown here, very well describes these principles. Okay. There's a question, why some multiplications star and other x? Well, these are two different operators. The first two operators denote divergence, and the third and the fourth operators denote curl or rotation. These are two different operators, mathematical operators, which describe the fields. How do the fields propagate in a three-dimensional space? That is why there is a difference. Okay, and before going straight to the integral form of these equations, let us take a look at a bit of history behind these equations. So these equations have been the first comprehensive summary of the electrodynamic principles together with the optics. So these combined the study of electricity and magnetism together with the optics. And actually Maxwell was the first who suggested that light is actually some form of electromagnetic wave. Later on it was proved in experimental way by Heinrich Hertz, who invented the first dipole antenna in his experiment, famous experiment, and obtained experimentally proved the speed of light and the existence of electromagnetic propagating field. But before that, Maxwell described the fields, the electromagnetic field, in terms of his equations, and this was not just a single work, but a series of papers which he worked on through the 1850s and 1870s. So in the course of 20 years, he was working on different subjects, and summarizing all of them, we got Maxwell, what we call now Maxwell equations. Actually, all these equations have been based on the works of such famous scientists as Michael Faraday, Emil Lenz, Franz Neumann, and André Ampère. By the way, Maxwell was a good friend of Michael Faraday when they worked together in London. So they were cooperating together, and many of practical Faraday's experiments have been the basis of the Maxwell theoretical work. Then later on, in 1994, the whole set of the equations from the Maxwell papers, there were 20 equations altogether. They have been summarized to just 4 of them and grouped together. And these 4 are what we now see as the modern Maxwell equations in different forms, a differential one or in the integral one. Yes, there is some other comments about this multiplication operators. Yes, that's correct. There's also another argument about this multiplication, so-called multiplication, but actually this is not just simple multiplication. These are different mathematical operators, as Kristaps described in his comment. Oh, sorry. Skipped all the slides somehow. Let us take a look at the integral form of these equations. First one, Gauss law for electricity, actually relates the dependence of electrical field on the charge denoted by Q, and the electrical flux out of any enclosed surface is proportional to the total charge enclosed within this surface. You can see there is integral of the electrical field through the area, denoted by A, and this is proportional to this charge, the total charge. How does this apply to the actual engineering sphere, engineering techniques? This finds application in calculating the electrical fields around charged objects, for example. And this is how we can physically apply this equation to a real world. The second one, the Gauss law for magnetism. And this is a little bit similar to the first one. However, we can see that the right part of this equation is 0. What does it mean? It means that there are no, as I mentioned, there are no magnetic monopoles. All magnets are dipoles. For example, if you take a magnet and you split it into parts, then each of these parts will be a separate magnet with its north and south pole. And you can do it to infinity. You can split these pieces further on, and you will get the separate magnets with the north pole and the south pole. And that is why any magnetic flux through the enclosed surface is directed inward toward the south pole, and it will be equal to flux outward from the north pole. So all the magnetic flux which is going out of the north pole gets to the south pole of the same magnet, and that is why the resulting magnetic flux is 0, like in this case. So there are no magnetic charges in nature. That is what physically this equation tells us. Yes, this is an example of a magnet, of a simple magnet. The third equation is the Faraday law of induction, and its name tells for itself, as this equation actually describes how the induction works. This is the basic law of electromagnetism, predicting how a magnetic field will interact with an electric circuit to produce so-called electromotive force. So it states that the line integral of the electrical field around a closed loop is equal to the negative of the rate of change of the magnetic flux through the area enclosed by the loop. You can see that in contrast to the first and second equations, here we have not A, not area, but S, which designates the length, the piece of inductor. So this is a bit different, and this equation basically describes the induction principle, the relevance between the magnetic induction and electrical field, which is generated as electromotive force. And it serves as a basis for explaining principles of electric generators, inductors, and transformers. So this finds very good application in engineering science, in applied science. And the last one is Ampere's law. The simple Ampere's law connects the current to the varying magnetic field, but with the addition of Maxwell's so-called displacement currents, it became the fourth Maxwell equation. So the first component by which the magnetic field can be generated is the current, denoted by I, and multiplied by permeability on the left side of this equation. Let me select the pointer. Here it is. And the second part of this equation, this was the addition of Maxwell himself. He called it displacement current. What it says? It says that the changing electrical field also produces the magnetic field. So it relates the electrical field to the magnetic field, just like the third equation above of Faraday's law of induction. Thus, we can say, and it can be applied for calculation of magnetic field for simple geometries also. So we can say that the third and the fourth equation basically describe how the electromagnetic wave propagates through the space, because they describe how the varying electrical field generates a varying magnetic field, and the magnetic field generates electric field, and so on. This is the main principle of how the electromagnetic wave propagates. So once we get to know how to describe the magnetic field, let us refresh our high school knowledge about the main features, main characteristic of a simple electromagnetic wave. What are these features? So the first one is the period. And the period is the time required for the electromagnetic wave to complete a full cycle. This is inversely proportional to the frequency of the electromagnetic wave. The second is the wavelength. And the wavelength is the velocity divided by the frequency of electromagnetic wave. And the frequency itself is the number of cycles per second of how often the electromagnetic wave oscillates. Also, we can derive the so-called velocity of electromagnetic wave. This is not the same as speed of light, because it depends on two variables. The first one being permittivity, and the second is permeability. If we take permittivity and permeability to be equal to vacuum's permittivity and permeability, which is denoted by epsilon 0 and mu 0, then we obtain the speed of light. So the velocity of electromagnetic wave is equal to speed of light in the vacuum, vice versa. The velocity in the vacuum is equal to the speed of light for electromagnetic wave. But if we take some other permittivity and permeability of other medium, then we obtain slightly less velocity of propagation. That is why the velocity of propagation of electromagnetic wave is not constant, it is not the same. It depends on the medium, and it depends on the characteristics of the medium. And the final equation, which could be useful for us, especially further on when we will be discussing antennas, is the power density equal to overall transmitted power divided by the area of sphere. All right, let us take a look at the spectrum of electromagnetic wave. This is the whole range, starting with the radio waves and going up to the cosmic rays. You can see the two scales. The upper scale is the wavelength, which decreases from left to right, and the lower scale is the frequency, which increases inversely from left to right. Somewhere here in the middle we see the visible light spectrum, and in the left part reside the radio engineering and the microwave industry, somewhere here. And if we zoom in this part of the spectrum, then we obtain something like this. And there is another division of the radio frequency range, depending on the length of the wave. The microwave actually resides somewhere here, from ultra high frequency to super high frequency and extra high frequency. So the microwave industry can be placed somewhere here. And our other radio engineering also uses the high frequency and the very high frequency for communications, for example, and also lower frequencies, but not that often. We can see that this frequencies up to actually X-rays and some part of ultraviolet radiation are non-ionized radiation. It means that it cannot change the DNA composition of human tissue. That means it's not harmful. More than that, the microwave equipment, for example, produces incredibly low energies of radiation. However, there are some TV transmitters operating in very high frequencies, for example, which are powerful enough to cause some damage to some part of human body. Namely, these are human eyes and testes. That is why there are some regulations by International Commission on Non-Ionizing Radiation Protection, which defines some regulations and rules about the maintenance services, about the safety and the operation of transmitters. Well, to zoom in the spectrum even further, we can see that extra high frequency part of the spectrum, as defined by IEEE institution, can be divided into V band, E band, W band, and D band. And these are also different parts of the spectrum which are quite important for the microwave communications, especially nowadays. This table relates the frequency to the wavelength. And we can see that a frequency of 300 MHz corresponds to the wavelength of 1 meter. This can be useful. We can derive a formula which allows us to convert the frequency to the wavelength and vice versa. Here is this formula, which I personally use very often. You still might need a calculator for this, but at least you are getting rid of this speed of light constant, and you can calculate and convert more easily. Here you obtain the wavelength in meter, and if you divide 300 by the frequency in megahertz. There is another question. Let me check. If light is electromagnetic wave, its speeds depend on environment in which it passes. It should be constant, no? Some stuff. Okay, there is some E equals mc squared equation mentioned. Not sure why in this context. But actually, yes, the short answer is yes, that the speed of light is also dependent on this propagating environment. And as we learned, it depends on permittivity and permeability of the medium, of the environment. And that is why the speed of light refracts when going from one environment to another environment with different, let's say, different composition of medium, different temperature, different pressure. That is why we observe the refraction of light, for example, and the refraction of any other electromagnetic wave. So the short answer is yes, it depends. And that is called the velocity of the signal, not to mix up it with the speed of light, which is constant and designated by c. And I guess E equals mc squared is related purely to this physical constant of speed of light, not to the velocity of a particular environment, in particular environment. And Kristaps answered also to this question. Yeah, basically the same. Okay, let us go on then to the next. And we now will observe the mode in which the electromagnetic wave propagates. the electromagnetic wave propagates in space in TEM mode, which is transverse electric and magnetic mode. What does it mean? It means that neither electric nor magnetic field oscillates in the direction of propagation, as we can see here. The magnetic field denoted by the red and the electric by blue. They oscillate perpendicular to the propagation, which in the axis of z. However, there are some other cases when this is not true. If we use the waveguides, for example, if we use the waveguide for transmitting the electromagnetic wave, then we have different modes, but the most common are transverse electric mode, when the electric field doesn't have the same direction of oscillation as the wave propagation, as on the left, as you can see on the left. And sometimes this type of propagation is called H mode, because relating to the magnetic field, which propagates along with the wave itself. And on another hand, we have the transverse magnetic mode, TM mode, which also occurs in the waveguide, and it means that magnetic field doesn't propagate the same direction as the wave itself, but the electrical field does propagate along the wave itself. And sometimes these modes are called E modes. And there are different variations of these modes in different types of the waveguides, but these are the main types, which summarizes basically most of them. And in this context, it is worth mentioning that the polarization of the signal corresponds to the plane of the electrical field vector. So we define the polarization as the position, physical orientation of the electrical field in space. Well, so this concludes the most confusing part, involving a lot of mathematics and a lot of equations. And I hope that it made it a bit clearer for you, and maybe more related to the real world situation, to actual physical phenomena. I wanted to make it more down to earth, to show that these are not some abstract equations, but they relate to the physics, to the physical laws we observe in our everyday life. Maybe not just visually, like we don't see electromagnetic radiation, right? But we know it is present. We can hear the radio stations, etc. And now we can see that this famous Maxwell equations applies to radio engineering directly, that it is related to physical processes which we use in radio engineering and in microwave technologies. And now I would like to remind you about so-called signal standards. And what does it mean, actually? It is not possible to imagine a conversation between two engineers, especially if we're talking about radio engineers or engineers in electronics. So it's difficult to imagine a conversation between them without mentioning decibels all the time. You know what I mean. So decibels are the most frequent measurement parameter for them, right? So why is that? So, and what stands behind this notion, all in all? Let us take a look. Decibels actually make it easier to plot and analyze data with enormous range. For example, if we evaluate the human hearing, which has extremely broad range, if we measure it from the threshold of hearing to the threshold of pain, it could be a range of 1 to 10 to the power of 13. So it's a large scale, and actually this is why where decibels have been used initially. Then another examples include a typical communication receiver, which process signals with the input powers vary from to the power of 10 to the power of 12, for example, and also the signal while reaching a geosynchronous satellite can be attenuated to the factor of 10 in the power of 20. So these are enormous ranges, and it's difficult to operate with them because we might need to take a value from the beginning of this range and from the end of this range, and they differ by enormous factor. So what do we need here? We need to shrink this enormous range to a smaller one, which could be more convenient to operate with. And that is why we might need a logarithmic scale. So basically, decibels, the main feature of decibels is using this logarithmic scale and relating one power value to another power value, measured in watts. The bell itself, which is named in honor of the telecom pioneer Alexander Bell, is denoted by capital B, and this is a logarithm of relation of two powers, while the decibel is the same value just multiplied by 10. And it is so if we are speaking about the power values. Well, in terms of radio engineering and microwave technologies, most of the time we operate with the power values rather than voltages. But if we need a voltage in the same notion, then we replace 10 by 20. And we get 20 times logarithm V2 divided by V1. If we're speaking about the powers, then we relate one power to another and multiply 10 by the logarithm of this relation. And from this one we derive the decibels that we need for comparing different values. For example, the input value of some device or black box, let's say, and the output value of the same device. Or if we want to compare, if we want to evaluate how our signal was attenuated during some processing or during the propagation, then we take one power value on the input and take another power value on the output or on the receiving side. We find the relation between the two, we find the logarithm of this relation, and we multiply it by 10. As an example, when we lose the half of power, let's say, or if we gain the same amount of power that we have on input, then we gain this 3 decibels. So 2 times equals 3 decibels in terms of power. And the same applies also to the attenuation. If we attenuate the signal by 2, then we lose 3 decibels. But all of these are relative values, so we relate one to another. These are not absolute values. We cannot say how much is 3 decibels. We can say that this is 2 times, but we don't have the absolute value of how many watts, for example. In order to operate with absolute values, as we need in the field of radio engineering, we need to relate this to a watt, for example, and then we get, okay, I forgot to mention that here are the table which gives you an overview of different power ratios to the decibels, both in minus and in plus. So you can take a look at this, and I will continue with the absolute values. So if we relate this notion to the watt, for example, then we obtain what is called dBW, or decibel watt. Actually, this is the absolute value in the relation with 1 watt. And the same can be done for the milliwatt, and then we obtain dBm, or decibel milliwatt. What does it mean? It means that, for example, 0 dBW corresponds to 1 watt, and 0 dBm corresponds to 1 milliwatt. And you can see the table on the right with an example. And in the field of microwave technologies, dBm are the most frequently used measurement values, actually, due to low power of the signals transmitted. Let me check the activity in the chat. Why dB is more popular than B? Decibels more popular than bells. What multiplication by think gives us? Seems redundant. Just historical. That's a good question, but I guess I don't know the answer straight away. Probably it was historical, or probably applying to the engineering sciences, it was more practical to multiply this value by 10. If we wouldn't do this, then, for example, instead of having 3 decibels, which we know is 2 times, we would have 10 by 10 times smaller value, which is not so convenient to operate with. So I guess maybe this is due to more engineerical applications. So this was more convenient for the engineers to use these values multiplied by 10. All right. If this is clear, I hope it is. Let us continue, and let us get to the summary of the decibel notion. We already learned about 3 of them. The first one is just decibels, and the decibels is a ratio of 2 power values on a logarithmic scale. So this is not an absolute value, this is just a relation between the 2. In turn, dBW is the decibel above or below a watt. So we compare our initial value to 1 watt. Is it strong? Is it how much? Is it larger than a watt or smaller than a watt? And then we obtain this dBW, or decibel watts. And that means that this actually represents the power, the absolute value, and it can be then converted to the actual value. The same applies to milliwatt. How do we obtain dBm? We just calculate how much dB the signal is above or below a milliwatt. And this also represents an actual power. And the final one I would like to mention is dBi, which is a decibel with respect to an isotropic radiator. This is also not an absolute value, this is a relative value, and this will be very important notion in our next presentation, when we will start discussing free space loss and isotropic radiator as an idealized source of radiation, as the mathematical abstraction. And we will also see how we can relate every antenna to this isotropic radiator, and how do we obtain antenna gain. So I will explain this notion in greater detail in my second lecture. So far I just wanted to mention that there is a notion of dBi as well. and it is directly related to the decibels. Another very good feature, very useful feature of decibels, that we can subtract them and add them easily. This is particularly important when we have a signal which propagates through different circuits, different transmission lines, and also free space, and we might expect some attenuation, some losses. So it is very convenient to calculate all the gains and all the losses. The gain can be from the transmitter, from the power amplifier. The loss can be from the transmission line, from the free space propagation. And for example, it is convenient for us to define the transmitter by the dBm or dBw, for example, in absolute values. And then it is convenient for us to define the loss in the propagation line with the decibels, which is the not absolute value but the relative value. If we wouldn't use decibels at all, then it would be very difficult to operate with these different absolute and relative values and to get the final value of the signal on the system output. But as long as we have decibels, it can be decibel itself, it can be dBm, it can be dBw. Let us just leave the dBw and stick to dBm because it is used more often in microwave technologies. So we can use dBm, we can use decibels, we can use dBi. All of them can be added and multiplied without, added and subtracted without any additional conversion. And that allows us to evaluate the loss in some system of propagation, let's say. As an example, we can view the link budget calculation when we add all the gains and subtract all the losses. This consists of 2 antennas and 2 transmitters and receivers on each side of the link, and the propagation occurs in the free space. In this example, this will be the Earth atmosphere. So we have dBm, by which we express the transmitter power. So we have a transmitter with a definite power on the output. Then, to get this transmitted power to the antenna, we use a transmission line. For example, coaxial cable or waveguide. Both of them has some degree of attenuation. And this attenuation is usually expressed in decibels in the datasheets. So we subtract decibels from this initial dBm value. And this is very convenient. We don't have to make any conversions. Then we add the gain of antenna. As I mentioned, this is expressed in dBi. This is another gain that we have. This amplifies our signal. While signal is propagating through the free space, it could be vacuum, it could be atmosphere, we observe free space loss. This will be the main subject of our second lecture. And this free space loss is usually also expressed in decibels. So we also subtract the decibels, and we perform the same steps on our receiving side. The receiving antenna is also involved here. So we can add gain of the receiving antenna to our signal. We can the same way subtract the transmission loss of the line, being waveguide or coaxial cable. And we have our dBm value on the output. So we can evaluate how does our signal was attenuated from transmitter to the receiver. This whole path can be easily calculated also without using some sophisticated formulas or even calculator. By the way, you will have a chance to do this yourself by taking a quiz. Okay, looks like this was it from my side, and we have some time for asking questions if they arose during the presentation. The question is, antenna can amplify the signal, a passive element, or there is some power amplifier? No, the antenna doesn't amplify the signal. That's correct, that this is a truly a passive element. There is no any power amplifier, and that is why this is not an absolute value, like in case of the transmitter we have dBm. Here we have dBi, which is relative, and this is relative to the isotropic source of radiation, isotropic radiator. And this is just how we describe how well the electromagnetic wave is concentrated in one particular direction. This is related to antenna directivity and to antenna gain. So this doesn't amplify anything. We just compare two situations. The first situation when we have isotropic radiator which propagates equally all the way outwards without any directivity at all, and we compare this situation, which is physically not possible situation. We compare this with a real world antenna with some degree of directivity and some gain. And every antenna directs the signal in particular direction, right? Well, if we are speaking about omnidirectional antennas, they are not omnidirectional truly, like not on the whole area of the sphere which surrounds it. There are some minima and maxima. That is why these antennas have directivity. So antenna doesn't amplify anything. The dBi just the way how do we evaluate the directivity, the direction in which the electromagnetic wave propagates, how much energy of electromagnetic wave is sent towards the desired direction rather than being emitted outwards to all the directions. This is gain, yes, this can be perceived as gain, but not a gain of the active element of any amplifier in that sense. If I have point-to-point with Rx take signal strength -40, -54 dBm and signal to noise 84 dB, how I should read this example? Okay, let us take a look. Received signal, what could you please specify what is the transmitted signal strength? So what is the output power of the transmitter and what is the received signal? Because I don't actually understand what does it mean Rx to take signal strength. Because signal to noise ratio is a bit different term. It cannot be directly applied here. Here we are not speaking about difference between the signal, the useful signal, and the noise. We don't consider noise at all. We're just speaking about the useful signal and how does it attenuate in the atmosphere or in the propagation line, transmission line. So the signal to noise ratio doesn't apply here directly. It more qualifies the quality of the signal, of how usable our signal is for, let's say, demodulation. So I would say that this particular example does not relate to signal to noise. It's just some absolute values of transmitted signal and received signal without taking into account any noise. So if you could specify your question, taking it into account what I said, that maybe I could try to answer. All right. Okay, so we will wait for your more detailed answer after the webinar here in the comments, and I will be able to answer here as well, because this video will stay on YouTube for your reference. So all the unanswered questions will be answered here. So if you happen to have a question after a while, you can post it here in this chat or in the comment section. Yeah, it's better to post it in the comment section, and then I will answer to your comment to this video. And finally, I would like to suggest you to test your knowledge, and you will see the first test in the description of this video, and I will also send it personally to my colleagues in the chat in MS Teams, which I created recently. Otherwise, thank you for your attention, and I will gladly see you next Wednesday with our second lecture on free space loss propagation. Thank you very much for your attention.